Not many that can say they can be on a floating studio, I suppose.
I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
the brain, life,
The universe.
Hello, welcome to The Naked Scientists with me, Chris Smith, and with Georgia Mills.
This week we're taking the show afloat because the quintessential way to see Cambridge, where we're based, is from a flat-bottom boat called a punt that you push along from one end with a long pole. And I think I can see ours has just arrived.
Indeed it has. The river that we're going to punt down is of course the River Cam, after which this city is named. And the River Cam actually flows past quite a few of Cambridge University's colleges.
Oh, it's quite windy, and that might be the least of our worries because we've now got to try and board a punt without dropping ourselves or any of our recording equipment into the cam, which wouldn't be a good start to the programme. Hopefully, once we get on the punt, we're going to stop off at each of the colleges to pick up passengers who are actually research fellows, and we'll be finding out what they work on.
The Naked Scientists podcast is powered by ukfast.co.uk.
Here is the guy who's actually going to do the very hard work of punting us downriver, and as we go you're going to tell us a little bit about the history of what we're seeing along the way. That's Max Thompson. You're from a relatively new punting company in Cambridge, launched in the last couple of years I think, isn't it? It's called Rutherford's. Why have you called it that?
Well, it's a connection to Ernest Rutherford, a graduate of Trinity College, known as the father of nuclear physics. The owner, Emma Wynne, is married to Jim Rutherford, a descendant.
And good for us, it sounds nice and sciencey.
Yes, absolutely.
But how many people do you carry on punts during the punting season in Cambridge? Because it's pretty busy here today.
Yes, this is the busiest time of year for us, the summer. The boats themselves have a maximum capacity of 12. Most of us are often in the summer days been doing 8 or 9 tours a day, so that would be around 108 or so customers we'll be interacting with in one day.
And when you take people on your punt tours, do you ever get tempted to tell them any porkies?
It can be quite tempting at times. Sometimes it's good to sort of have a bit of a joke and see how far you're willing to take something. Because Cambridge itself is a very ridiculous place, to the point where you could make up a porcupine, but it sounds legitimate enough that it could have actually happened given the right circumstances.
So is this our punt that we're going to go in?
Yes, it is. If you'd like to join me, we'll have a bit of a wobble.
In. I'm in.
We've got to
Watch your
jump
step, Georgia.
over another punt to get into this one.
Georgia's aboard.
Okay, we've made the first step.
You mind the wine glasses? I see that we've already got the bar open on board, which is quite good.
The studio is now well and truly afloat, and we're just at the part of Cambridge down by the mill pond. There's a sort of big lakey area full of willow trees and a lot of other punters who I imagine we'll be crashing into sooner or later. So Max, where are we and where are we going?
Well, at the moment we're at the Mill Pond area, as you mentioned. It was one of the major hotspots for punters to have their tours begin. But we're also next to Darwin College, just over there, one of the newer colleges on the river, of course named after Charles Darwin. And then to my right-hand side we have the old Anchor pub as well, formerly known as the Jazz Club, and it was actually where a small band you may have heard of, Pink Floyd, played their very first gigs back in the 1960s when Syd Barrett was the lead singer.
Well, we're now going under the bridge. This is the bridge next to the pub. Which road is above us now, Max?
So it's Silver Street, so this would be Silver Street Bridge, hence the association. This will often be where most tourists will be standing to view the mathematical bridge and also to watch the most punts crash into one another, because this is generally a turning point for most chauffeurs to go down to the other side of the river, and so they'll be bumping into self-hires and everyone bumps into one another, so it gets a little bit chaotic, shall we say. We're now arriving at Queen's College here, founded back in 1448, in part by one Margaret d'Anjou, the wife of King Henry VI, who founded King's College, which we'll see later on. But then we've just gone underneath the mathematical bridge here, designed back in 1749 by a student of Isaac Newton's called William Etheridge and built by David Essex. So if anyone tells you it was designed by Isaac Newton, they're lying. We're about to pick up our first guest, so I'm going to find ourselves a nice spot to park up and get him on here safely.
We're just manoeuvring into the side here, and there is teetering on the bank above us our first passenger. Welcome aboard.
It's a long way down.
It's a very long way down.
Thank you.
Welcome to our studio.
Thank you.
My name's Graham McShane. I'm a fellow in engineering at Queen's College, and I'm an academic in the engineering department. So I lecture and do research in topics in engineering materials.
And we've just travelled under the very famous or infamous mathematical bridge that Max was just telling us about. Unlike most of the bridges which are kind of solid, this one is like a crosshatch kind of design with lots of wood and poles, loads of geometric shapes that you kind of look like you could sort of fold it up like a duplex kind of structure. So why is this bridge, apart from looking great, why is it special?
It's very unusual amongst the bridges that you see behind the colleges on the river. As you mentioned, all the other bridges are solid stone arches, but the mathematical bridge is made out of wood, is the first thing to notice about it. And the reason you can get away with making it out of wood is that it's a totally different kind of bridge. It's what's known as a truss structure. So a truss structure is made up of a whole series of bars which are linked together, and they transmit the forces very efficiently to the supports. And so by using a truss structure, you can create a structure which isn't necessarily as strong as a solid stone arch, but it uses little material. It uses the material very efficiently, and so it transmits the forces to the supports very efficiently. So you have a very lightweight structure.
Right, and this is why it can be not so solid as all the others.
That's right. And what's also unusual about the mathematical bridge is not just that it's a truss structure, but it's an arched truss structure. So you very often see trusses used to build things like railway bridges. In those cases, it's a flat truss structure that goes straight across the river. But the Queen's Mathematical Bridge is an arched truss structure, and that's quite difficult to achieve. And so the bridge uses a very distinctive way of arranging the bars called radius and tangent trussing, and that's a way of achieving this curved truss shape.
Uh-oh. Being attacked by another punt. We're trying to have an interview here.
We're going to be boarded in a minute.
Do you get punt pirates? Is that a thing? So it's a very impressive structure, and it seems like it's a great idea if you want to save material. You're an engineer. Do you use this structure in your work?
Well, truss structures are obviously of interest for efficient, lightweight structures, and saving weight is very important in mechanical engineering design because people want lighter aircraft, lighter cars, lighter trains. And so there's a whole area of research looking at how you can create materials using the same concepts. So if you imagine taking a truss structure like the mathematical bridge and miniaturising it down until the bars are a few millimetres in length, then you've got a material that's known as a lattice material. So a lattice material is a type of material where it's made up of an array of bars distributed to transmit forces very efficiently through the structure. And so this allows you to create very stiff, very lightweight materials that are very good for lightweight engineering design. They also have other interesting properties. So when you crush these lattice structures, they absorb energy very efficiently. So they can also find uses in things like crash protection and also in helmets.
Another Cambridge favourite, cycling then?
Absolutely. So people want lightweight, efficient helmets for sports and for cycling and all kinds of other applications. And so we're very interested in using lattice materials to create the next generation of protective equipment and helmets. So maybe in future you might see a helmet that when you cut it open it looks like the mathematical bridge inside.
Graham, do you see the same sorts of structures cropping up in nature? Has nature engineered its own solution using the same physics?
Absolutely. So if you look at the structure of the bones in birds' wings, for example, those are very stiff, very lightweight structures where they've got a complex network of bones within the bones. So you've got this truss-like structure which gives you that stiffness and lightweight. So you do see it evolved in nature in any applications where you want to save weight but still has to be stiff and strong at the same time.
And Max alluded to the fact that there's an often heard rumour that Newton built this bridge. What is that rumour and why do we know it's not true?
Well, it's a good story, but unfortunately it doesn't have any basis in facts. The main reason why it can't be true is that the bridge was designed and built long after Newton died, and so he couldn't have had anything to do with it, unfortunately.
He was clever, but he wasn't that clever.
He wasn't that clever, that's right. There's also stories that it was designed by a student of Newton, but that's not true either.
Separating fact from fiction, Graham McShane, thank you very much for joining us on our Punt studio.
No problem, you're welcome.
So we're now arriving at King's College, founded back in 1441 by King Henry VI, also known as the Mad Young King, was often thought to be the inspiration for King Joffrey in Game of Thrones. But ironically, the college itself was first set up as a finishing school for Eton graduates, but these days actually has the highest population of state school students in Cambridge. We also see the King's College Chapel just here, looking rather splendid and glorious. Actually the second largest chapel in Europe, only being beaten by the Sistine Chapel at the Vatican, because everything's bigger at the Vatican, of course. Meant to take only 10 years to build, but thanks to said War of the Roses, took 90, which isn't as bad as Sagrada Familia in Barcelona, but still nothing to brag about either, I suppose.
Anything else notable about King's?
Well, the most notable alumni from King's is, of course, one Alan Turing, known as the father of artificial intelligence and modern-day computers, and basically helped us win World War II.
And we have some people waiting for us on the lovely lawn in front of King's College, next to the giant sign saying no mooring. We have 2 more special guests, so let's find out who they are.
I'm Herbert Huppert. I'm a theoretical geophysicist here in Cambridge, and I'm interested in the environment and how volcanoes erupt and how we putting in far too much carbon into the atmosphere, and we'll live to regret it. Or I hope we'll live.
Funnily enough, when we were announcing our arrival and we phoned you up and we said we're going to be about a little while, and you said I'm a geologist, that could mean millions of years.
Yeah, well, the Earth has been around for quite some time. You and I are very recent, even humanity's a very recent introduction, and timescales differ from the Earth to what you and I are used to thinking about.
And who's our other passenger?
Jules Griffin from the Department of Biochemistry here at Cambridge. I work on aspects of type 2 diabetes, in particular the interactions between our diet and relative risk of developing type 2 diabetes.
So we'll be toasting our alcohol and talking about our health later.
Yes, indeed, yeah.
So Herbert, let's talk about the health of the planet first before we talk about the health of the people on this punt and the wider society. Amazingly, 10 years ago, you and I did almost the same thing as we're doing today, because we did a punt trip down the Cam and we chatted about the subject of carbon in the atmosphere, carbon sequestration and so on. How has your view today, 10 years later, compared with your views 10 years ago? Has it sort of played out the way you expected?
I remember the punt trip, but not what I said 10 years
ago. I was going to say it's age.
I'm only 21. But things have got much, much worse. I don't remember the exact figures 25 years ago, but something like 27 billion tonnes of carbon dioxide were put into the atmosphere by mankind. Now it's 37 billion tonnes, and increasing all the time.
Every year?
Every year. The mean global surface temperature is increasing all the time, and we're seeing great problems. This is not a great problem, but we see it how dry and hot it was this summer, and the King's Lawn, which is just on my right, was absolutely parched. Well, do we want it to be parched? Do we want to have a parched Earth?
But many people argue that the Earth goes through cycles, that it's been doing it for millions of years. This is just one of its cycles, that the tiny contribution of humankind is not driving that process.
Well, those people that argue that, I'm afraid, are not correct. It's true it goes through cycles, but this is a man-made cycle. This is putting a huge amount of carbon dioxide into the atmosphere, much more than volcanoes do or natural events, and it's putting it in very quickly. There's a dramatic rise over the last 100 years, which is a time scale. As I said, I'm a geologist. Before, the time scale was a million years. Now it's 100 years, and getting much worse over the last 10 years.
If we keep going like this and releasing carbon dioxide, what will be the consequence?
First, there'll be larger variations in weather, going from hot to cold. The general temperature will increase by a few degrees. Also, what's a problem is that the sea level will rise, and it will make life very difficult. Now we're in Cambridge, this used to be pretty close to underwater in the 1400s. We could end up in the 2100s being underwater. Bigger problem, of course, I'm just talking about Cambridge, is places like Bangladesh that could be totally flooded. Immigration is not liked. How will it be when thousands, millions maybe even, of people lose their homes and their countries? Who's going to take them in?
Now, one of the things that we know has had a profound effect on the climate over long-term geological timescales on Earth is things like tectonic plate movements, which make mountains, and this displays to the atmosphere minerals that can pull down carbon dioxide, and that changes the CO2 level in the atmosphere. Is there a way that we could mimic that process to wind the clock back and undo some of the damage we're doing? And is it practical?
Well, that's a brilliant question, if I may say. Over the last 40 years or so, people have talked a little bit about taking carbon and storing it in the earth, sequestration. But just very recently, it's been suggested, and I want to do some research on this, whether mineralization could be speeded up. We know that rocks take in carbon dioxide, just as you say, but that's on a geological time scale, millions of years for which we had to wait for this punt. But the question is whether we can influence things so that mineralization can happen much more rapidly. And that's an interesting question. Please invite me in 10 years' time and I'll give you a very positive reply, I hope. But I don't yet know, other than I have a very capable geological colleague at Columbia with whom just over the last few weeks we've been talking about whether we could do something together in just that area.
Also the question of whether we can draw the CO2 out and rather than turn it into minerals, put it underground in places like where the oil and gas came from, which obviously is geologically very stable, it lasts for millions of years and would be able to hold it and hold it safely.
Well, that's has been the idea for some time of carbon storage. There have been a number of experiments. They've all been pretty successful when they're field experiments. We've done lots of laboratory experiments, and by and large they've been successful, but laboratory experiments are not meant to be successful all the time. You often learn from what isn't successful. But the field experiments have been successful. The total amount at the moment of carbon dioxide that's taken out of the atmosphere and stored in reservoirs around the world is 10 million tonnes a year.
10 million?
10
so we're
million.
Releasing on the scale of billions, but
Yeah.
we're drawing down only on the scale of millions.
That's right. 10 million versus 37 billion. And one of those figures is rather smaller than the other.
Yeah, we're 3,000 times smaller, give or take, isn't it?
Yes.
Yeah. So it's not practical.
No. Well, that's an interesting question. Could it be done? Yes. Could countries get together and companies get together and store carbon dioxide successfully at the rate of, say, 20 billion tonnes a year? Yes, I think it could be done. There's easily enough space, reservoir space in the earth. Nobody seems very enthused. Ask Mr. Trump and he'd say under no circumstance. Ask Mrs. May or Boris Johnson, they wouldn't be in favour.
On that gloomy note...
let me tell you some good things.
well, good things. These strawberries look rather good. Do you want one?
Oh yes, I'd love one.
I'm also joined by Jules Griffin, so we're drifting along the Cam, eating strawberries and sipping knockoff fizz. So tell me about diet.
I think the basic message is that as human beings, we're probably eating too much in the Western world at the moment. So my research is looking at the interactions between diet and chronic metabolic diseases, so diseases like type 2 diabetes, cardiovascular disease and fatty liver disease, and diet is a major component of those diseases at the moment.
Why is eating too much food bad for you?
As animals, we've adapted very well to storing food and going through periods of relative famine and fasting. And the body's geared up for doing fasting and conserving those carbohydrates and fats until we need them. The problem comes, though, when we can eat continually and we can basically graze or have much bigger meals, that we're still very good at storing fats and carbohydrates. And probably the limiting factor is what our skeleton can actually cope with in terms of that storage. And this has dramatic sort of health effects if we eat to excess. We're also not doing as much exercise, unlike the chap that's punting us along at the moment.
Not like us though, we're being lazy.
Exactly, and I think that's really the key thing, is that we're drinking things with plenty of sugar in them, or eating things with high saturated fats, and we're not doing enough exercise.
So how are you looking into this?
We look at blood plasma and urine samples from people. Blood plasma is basically the bit of blood after you've taken out all the cells. So this carries a lot of nutrients around the body, so sugars, in particular glucose, fats and also amino acids. And the body needs these things in order to cope with the day actually and get you through the day, and also during processes like growth. But at the same time, you don't want to have too much of these because they have to be stored somehow. and if you have too much of these, they get inappropriately stored across the body. So you tend to see them less in our fat cells and more in things like the liver and muscle cells, and that's how we get insulin resistance and then type 2 diabetes.
Right, so how does sort of looking into this help us? I don't know, can we stop diabetes in its tracks?
Actually, there is some good news there that I think if we'd have been conducting this interview 5 or 10 years ago, we would have said that actually type 2 diabetes is largely a one-way street. But there's been some really interesting research into gastric bypass surgery, where you can show that just by the fasting associated with gastric bypass, you can reverse a lot of the effects of type 2 diabetes as part of this. We're interested in trying to understand why certain people are predisposed for developing aspects of metabolic disease and other people are protected. So we're looking at some of these small metabolite markers to try and pick out populations that are either at risk or are protected, to understand some of those protective mechanisms.
Right, and is that a sort of genetic thing or environmental?
We know it's partly genetic and we know it's partly environment as well, so with food being the biggest component of that, environmental factors. We've done quite a lot of work in terms of fatty liver development, and the bad news there is that alcohol is a big risk factor, but also yeah, I'm guilty of that as well. But also just sugary drinks as well, potatoes and crisp-based products as well.
The thing is, a lot of what you're saying hasn't really changed dramatically in the last 5-10 years. And if you look at children going to school, a record number of them, like a quarter in Western countries, are now overweight or obese at the time of starting school. It's a really frightening number. So what has changed that we are so dramatically different than we were when young people, say 40 years ago, were going to school, when that number was a fraction? It was a very tiny number that were overweight.
I think there's been two big effects that we've seen sort of happening. One is a reduction in the amount of exercise. So exercise, is amazingly protective even if you don't reduce weight, actually, in terms of protecting against type 2 diabetes and the complications associated with type 2 diabetes. I think the other big problem is just the availability of foods that are very high in sugar. The good news is that we've probably done a pretty good job as a nation in reducing some of our saturated fat content intake. We need to go further in terms of that, but the bad news is that we're probably eating more calories, and the body's very good at storing those calories, so that's how you see more people being overweight and more obesity.
So if you've got this fatty liver change and then you embrace a much more healthy lifestyle, will it go away?
That's the good news. Yeah, it does go away in terms of, if you can do things to reduce your food intake, or I try and go out on a run a bit more often and do it the other way around, as I have quite a healthy appetite.
So what if you run to the pub? We're going to have to chuck you out now, Herbert and Jules. So thank you very much for joining us and imparting your wisdom. We'll see you in another 10 years and we'll find out if carbon capture and storage has actually moved at all, because I don't think much has changed since we last spoke, really, is it? Now mind the gap on the way out, especially after all that Prosecco. You've drunk us out of house and home and eaten all our strawberries. Ironic, since you were here to talk about diet and health.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
And here we are at Trinity College, which has to be the largest and richest college in Cambridge, these days worth an estimated £1.3 billion. This is largely down to the fact it was founded by King Henry VIII, he himself the largest and richest king the country's ever had. And when he passed on 5 weeks after founding Trinity, he left quite a bit of money and land he had stolen from the Catholics to this college. Very sneaky. But it meant that Trinity was able to establish the empire for which they now sit upon, as they are also the third largest landowner in the country as well.
And what's this lovely building on our right?
This building here is the Wren Library at Trinity College. It holds around 70,000 books and texts inside, designed by Christopher Wren, the man behind St Paul's Cathedral in London. All the books in this building will be on the top floor, just in case of flooding, which does happen from time to time in Cambridge, as we are below sea level and quite flat. In fact, the year this library was intended to be designed, 3 floods affected the town. So it's not so much paranoia as precautionary.
Well, if Herbert Huppert is right, that's some very wise steps they've taken.
Absolutely. And then you have the top floor as well, has these tinted windows which actually block out ultraviolet rays from the sun, because if the books are exposed to natural sunlight for more than 3 hours, the ink inside will disappear.
I know that well because I had a signed copy of Harry Potter and I left it on my bookshelf and it got bleached and it's now worthless.
Isn't that? Oh, that is just the greatest tragedy of all.
If only I'd kept it in the Wren library.
There we go. Maybe next time. Well, if it was kept in the library, it'd be among a lot of other wonderful books. Maybe not as entertaining as Harry Potter, but some notable examples are Sir Isaac Newton's handwritten copy of the Principles of Mathematics. It's the very first edition, so it has all its annotations, and it therefore as well has the very first written down theory of gravity. So that's pretty significant, all things considered. You also have the Capella editions of William Shakespeare's plays, the first translation of the King James Bible, and you also have the most important book ever written in British history, which has to be the very first handwritten episode of Winnie the Pooh, of course.
So how's he going to top Newton? But yeah, Winnie the Pooh does.
There it is.
And so he's got some very famous books. What about Trinity College's famous alumni?
Well, you got around 32 Nobel Prize winners, which is higher than some countries, just say. But in terms of the most notable, I feel it'd be amiss to not mention, of course, one Sir Isaac Newton, who would discover gravity and the speed of sound while he was here. He started off as an undergraduate, then he was a postgraduate and then a professor, and then he was also the Member of Parliament for Cambridge University.
Member of Parliament? Sorry.
Yes.
For a university?
Until the 1930s, Cambridge actually had 2 MPs, one for the town and one for the university itself, because that's how much nonsense was here.
But we don't have that anymore.
Not anymore, at least not officially.
And I think I can spy 2 of our next guests waiting very patiently for us by the bridge. Our guests are on the wrong side of the river, though, unfortunately. There, they found a bridge.
Right, welcome aboard. Strawberries and champagne. Look, we've got that, and champagne, yep.
I'm Chris Lowe. I'm Director of the Cambridge Academy of Therapeutic Sciences, ex-Professor of Biotechnology, and I'm technically retired now.
I'm Amanda Prorock and I'm a university lecturer in the Computer Science Department.
Now, Amanda, we should just point out that actually you're not from Trinity, but you're from a college that doesn't have the river running past. So we've let you on board at Trinity.
Correct.
Welcome on board all the same.
Thank you very much.
I mean, you can't have everything. You can't have a fantastic college and river frontage. But you can have a glass of Prosecco.
Well, very kind, thank you.
You expect anything sensible out of me then, in that case?
Well, Amanda, so far you've just joined us, but we've had quite a few crashes and collisions, but maybe you'll be able to help with that. So first off, tell us about you. What do you work on?
So I work in an area called multi-robot systems. I deal with the development of algorithms that allow multiple mobile robots to operate in a coordinated manner.
Wow, so like a swarm of bees all moving and not crashing into each other?
In a certain sense, yes. So some people like to call this collective intelligence. Basically, the idea is if you have multiple intelligent entities communicating and cooperating with each other, you can achieve things that are more than just the sum of the individual parts.
What kind of applications could you have for a system like this?
So I think that traffic and transport is currently a very interesting application. There's a lot that we can do to improve traffic as it is given today. I mean, you look at what's going on the river today and you see everybody's just kind of doing their thing and we're randomly avoiding other boats. Nobody has a clue of what the optimal maneuver here would be. And if we would just add a little bit of intelligence to the system, we would probably be maneuvering in a much more smooth, efficient, and actually also safe manner.
No offence, Max.
No offence at all. So basically, you can think about how humans navigate traffic, and there are 2 ways we do this. Either we have reactive behaviors, which is we kind of detect what's happening around us. There are boats, vehicles to the left, to the right, to the front, to the back, and we either nudge a little bit to the left, to the right, we brake, or we accelerate. So that's one manner. The other way we deal with traffic is in a little bit more of a deliberative manner. So I can see a boat coming from the front, or I can see a boat coming on the left, and I can try to make a guess or an estimate about where I think that boat is heading. And based on that, I can kind of make a little bit of a plan towards where I want to head so that I will probably not collide with that other boat's plan, which I have kind of mapped out in my mind virtually. And so this kind of deliberative thing is what we can take many steps farther if we actually add technology. So you can imagine that these boats here could be planning their paths all the way from the start to the end, to the goal, and they could communicate these plans to all the other boats that are in the vicinity. And you wouldn't even have this kind of these maneuvers that you see happening here, because the plans are all laid out and they've all kind of smoothly negotiated how they're going to be getting around each other.
Right, so what are the big challenges involved in systems like this, either for punting or for cars?
So I say there are two. One is scaling these systems up. So obviously, if this punt or this boat here has a plan where it wants to head, it's not going to communicate this plan to all the other 100 boats on the cam. So you have to decide whom you want to communicate this plan to. Obviously, communication bandwidth is one issue here, and also computational resources are another. The other aspect is actually when we communicate our plans to other vehicles, we're assuming that they will take these plans into consideration and they will cooperate with these plans. So I'm saying I'm going to go this way, the other car will then try to find a path that goes around that path and not into that path. So we're assuming implicitly that everybody else is going to cooperate with us. So this underlying assumption that everything is cooperative is somewhat of a strong assumption for two reasons. Other boats or other vehicles can be compromised maliciously, or other boats or other vehicles can simply break. The communications may suddenly not be up and running anymore. And so we can't really ever assume that other boats are always receiving our plans and are going to act upon them as we think or hope they would be.
Right. And no offence, Max, don't listen, but could we use technology and robots to replace our punter, do you think?
Don't worry, my lips are sealed.
It would be a very sad thing. Actually, replacing the punter with a similar mechanical design is probably not the most efficient thing to do. You'd probably want to put a motor into the water that propels us forwards. If you would want to have some sort of robotic arm that pushes down into the water and hits the ground and pushes us forwards, I do think that would be quite challenging because you need to have precise force feedback, and I'm not quite sure what the sediment looks like at the bottom of the river, but I don't think it's solid. So this would involve sensing technology that is resistant or capable of functioning in those kinds of environments and able to give feedback.
Right, so your job is safe for now, I think.
Amanda, can I ask you, will I still be sitting in a traffic jam on the way to work if we implement your system? That's what's going through everyone who's listening to this mind, I'm sure.
So throughput and congestion control is one of the things that we can get rid of with more automation in traffic. And it's not only about making cars autonomous, it's also about connecting cars to people and deploying ride-sharing systems where we're better using the capacity of cars that can actually carry more than just one human driver. And we can do this by implementing systems where cars are actually perhaps not privately owned anymore, but are similar to what we see happening with Uber and Lyft, being driven around cities in a shared kind of paradigm, and humans can just hop on and hop off on routes that coincide with the routes they would be driving normally with their own private cars. I think this is a much more efficient usage of the actual resources that we need to actually produce cars. It's a better resource of real estate because the cars don't need to be parked anymore. So I think there's a huge potential to improve over multiple dimensions here if we would implement such systems.
Are the problems you're trying to solve and grapple with equivalently tough, Chris?
They're always tough when you're dealing with healthcare. You're dealing with patients, you're trying to diagnose difficult sets of circumstances, and of course the treatments don't always match that either. So yeah, it's equally challenging, I would say.
You're in an interesting space because how many companies is it you've spun off?
I'm on my 12th one now.
What do they all do?
They're in various sectors. I mean, my research area has been healthcare biotechnology in general, so that covers both diagnostics and therapeutics. So the companies span that thing. So we have one company working exclusively in the area of diabetes. We have others that are looking at other types of therapeutic modes. Others are in diagnostics area and so forth.
I did read somewhere that haven't you got a contact lens that monitors blood sugar?
Yes.
For diabetics?
We were the first group in the world to actually test it with a real person. We gave that person 180 grams of glucose, which is the standard glucose tolerance test, and then we monitored both the blood glucose and tear fluid glucose, which is where the contact lens comes in, and we demonstrated there was a correlation between the two. We've only ever done it with one person. That was published in 2006, and nobody's ever done it since.
What does the contact lens do, and how does it signal to the person what their blood sugar is?
Well, you're well aware of a soft contact lens, presumably, a daily wear contact lens. That's made out of a polymeric material, and what we do is we incorporate in that a volume hologram. Now, a volume hologram is not like the one you find on a credit card, which is that's a surface relief one, okay? With a volume hologram, we can produce layers of metal particles or layers of polymer which create a diffraction grating. So when you put white light in, it actually only releases a single wavelength back out of it, and therefore it looks a coloured one. Now, if we can change the spacing of those fringes within the hologram, within the grating, we can change the replay colour. So the idea is that we put the hologram into a smart polymer which has a receptor for binding the glucose. That binds the glucose, you get a change in fringe spacing, hence a change in wavelength that's replayed out of the hologram. So in other words, the hologram looks a different colour, and we monitor that colour.
So the diabetic would have some extra sugar in their blood. That would end up in the tears.
Correct.
That would then enter the contact lens and change the thickness or the size of this grating, which would affect the way that the light that's going through it bends, and you'd end up with them seeing a colour, presumably.
Yeah, well, the patient won't see it because it's in the eye, don't forget. So we're using a mobile phone then to actually monitor the colour in the contact lens, and then convert that mobile phone response actually into a concentration.
So they know how much insulin to administer or not?
Exactly, that's the idea. Yeah.
Does it work?
It works in principle, and I say we have tried it with one person, but of course you've got to do major clinical trials on this because people's lives depend on it, so you've got to do a significant clinical trial, which we've not done yet, but we plan to. I did bring some of our sensors along with us if you're interested.
Have you got some?
I've got some in my pocket. This is one of our holographic systems we've been developing. It's the same sort of hologram that we put actually into the contact lens, but you see this is used for a slightly different thing. It's an authentication sensor. So if you've got an expensive piece of, you might have an expensive handbag, for example. Not that you have.
Yes, I definitely have, Chris. I have a very expensive handbag, especially at weekends.
And you want to know that's an original one, you could put a hologram like this on it. And this is a breath-activated one. In other words, it changes as you breathe on it, all right? Now, if you see it on there, it has SH on there. That's one of the companies I was involved in, Smart Holograms. If I breathe on it, you see it's got little green.
Gone green with ticks.
Little ticks on it, exactly. And that's changing one hologram for another.
So go on then, let the cat out of the bag. How does it work? Because all you did was you went sort of and huffed a couple of breaths onto the red colour which says SH. It turned into a whole bunch of little arrows looking green. So
this actually has two holograms in it. Okay, one starts off in the ultraviolet, and the other one starts off in the visible region. So this first one, where it says SH on it, that's in the visible region. Now, what happens is when you breathe on it, the moisture in your breath, which is water, actually expands the hologram slightly. One hologram moves then from the visible into the infrared, so you don't see it, and the one that's hidden in the ultraviolet moves into the visible. So you get replacement of one hologram for another.
That's ingenious.
And our final destination is now Magdalen College. Please keep your arms inside the vehicle until we have come to a full stop. Thank you very much.
Well, look, it's been lovely having you aboard, but we're going to have to boot you out. We have arrived at our next destination. And so, Chris, thank you very much. Chris and Amanda, thank you.
So before we reach Magdalen, we get past the back of the new course, which is covered in this beautiful Boston ivy, which in the autumn turns a very beautiful, intense red, known as blazing red, which the sports team of St. John's decided to use as the official colour for their formal jackets, which because of the blazing red, they then became known commonly as the Blazers. And you can see where I'm going with this. Dun, 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 dun. The term blazer would then be adopted to the jacket itself. Ta-da! Don't you feel so smart?
So is that really where we get the word blazer?
Yeah. That's why a traditional blazer is normally red, because it matches the blazing red of the Boston ivy.
He did say earlier he likes to fib, though, so I think we might fact-check this one.
Look out for alternative facts and fake news on here.
Of course.
Oh, I think I see a guest.
You're most welcome aboard because you have a picnic basket. We're rather hoping it's full.
Oh, it's a heavy goodie bag.
There's a few things in there, yes.
And take a seat.
Always be prepared. Hi, I'm Alex Tom. I'm a fellow at Magdalen College, and I'm a theoretical chemist in the chemistry department here.
So tell me a bit about your work. What do you work
So theoretical chemistry tries to do chemistry mostly in a computer. That is quite hard because there's a lot of atoms involved in chemistry usually. And so I work on making that better, basically, by designing algorithms to enable us to solve the problems more easily on today's computers.
Why does it help to do the chemistry on a computer instead of a dish?
Sometimes you just can't do the experiments. Let's say you want to look at the chemistry in the atmosphere of Jupiter or in the sun, or even, let's say, you've got a lot of different materials you want to screen for some exciting property like a solar cell. It's just not economical to do these experiments, or not possible. So if you can get answers from a computer, that can at least help.
And why is it difficult?
It's all to the blame of physicists, really. So we need to solve the quantum mechanics underneath chemistry, and basically every electron in a molecule is entangled with every other electron, and you need to take into account all of those correlations, and that gets really horrible very quickly. Yeah.
Right, so it sounds like tricky work, which might bring us on to your other interest, which is also chemistry related. So tell me about that.
Yes, so I've had an interest for some time in wine and enology, which is the sort of study of winemaking and tasting wine.
So does that mean that inside this basket there might be some wine?
There are a few bottles of wine in here, yes, and other jollities. So I brought a few bottles of different wines, and it would be nice to try them and possibly even do some science on them.
Possibly, maybe. Mainly drink them. Excellent. So how does chemistry come into wine tasting then?
Certainly in winemaking, there's a great deal of chemistry. A lot of vineyards will have their own enologist, who's basically a chemist. When you start making the wine from the grape juice, a lot of things can go wrong, and you need to be able to study it quite quickly and fix them. And to make products that are nice to drink isn't easy, so the more you know about what's going on in your wine, the better. The flavour profile is made up of hundreds of different molecules. The main components are alcohol and some acidity and water, but the interesting bits are the flavour molecules, which are very difficult to isolate and put together, and vary from year to year, from grape to grape, from wine to wine.
I know these are things when someone will say, oh yes, it's got hints of oak or something, that's the flavour molecule doing that.
Exactly, it's tastes of guava or pineapple, or you can smell cut grass or that sort of thing. All of those are volatile molecules that you get when you smell it and also when you taste it.
This has all got my mouth watering. Yep. So perhaps what's the first one we're going to take?
So I brought an interesting wine here called a Riesling. That's the grape, and I chose it because one of the important constituents of wine is the acidity. That's what often makes the juicy feeling in the mouth for wine, and I wanted to play with the idea of changing the acidity of wine and to see what the flavour changes as.
Oh, so we can actually change the acidity, even though it's already been made, put in the bottle, we can tinker.
The joy of chemistry is that we can play with some of these elements in a controlled fashion. Let's try it as it is, okay. And we can comment on it, and then I can tell you what the official tasting notes say.
I love this. You can tell you're a chemist, Alex, because you've got a Pyrex beaker that you're going to drink exactly. This out of.
Actually, I got this at the International Chemistry Olympiad this year, so that was a gift there. It's great.
It's fantastic. It's literally a Pyrex like you would put on a retort stand on a gauze or something and boil away in a laboratory, but it's got a handle on the side.
So I'm going to put a little of this Riesling in the glasses first. This is the unadulterated wine, as such, and we'll taste that. Give it a swill in the glass, and maybe get some of the flavour out.
I think it's a bit smoky, it's a bit flowery, and maybe a bit of citrus.
There's citrus in there. The flowery is good. I can't get the smoke myself, but
maybe someone went past smoking.
Yeah, exactly. There are all manner of things in the atmosphere. But again, everything's very individual.
It is quite sharp. I'd say that's quite an acid wine.
It is, yes. So I picked it because it's a Riesling which is known for one of the most acidic wines. That can be good and bad. People like acidity in wines because it means they keep longer, they age longer. But if it's too acidic, it just becomes sharp and horrible. So this is a wine you might have on a sort of hot summer's day, like today, and the acidity makes it feel more refreshing.
Very, very nice. So can we see what happens when we change that acidity then?
Right. Yes. So I'm going to do a little modification of the acidity here. So I poured some of the wine into my beaker, and I'm going to add to it some bicarbonate of soda. Now this is an alkaline salt basically. It's just a standard kitchen chemical, but because we're on a punt, it's quite difficult to judge quantities and do this correctly. So into this wine, I'm going to cheat and add a little bit of a homemade indicator. So I made this out of red cabbage last night. Hopefully it won't change the flavour too much. But this wine is currently a nice sort of yellow colour, and if I add a bit of this, it should change to a startling pink colour. Hopefully there, right. And I can use this indicator to tell me how acidic the wine is. So this very pink colour means it's pretty acidic at the moment.
Right, and it goes bluer when it's more alkaline.
So it currently looks like rosé, doesn't it?
Yes, exactly. So I'm going to now add to it some bicarbonate of soda, and hopefully that should fizz quite happily there. And it's gone a bit darker purple. So if it goes, so we're looking for a purplish colour rather than a green colour. If it's gone too green, it's gone too alkaline. Right.
I mean, it feels like the acidity may have changed, but we've also put in cabbage and a lot of soda. So is this really going to tell us?
That's a good question. So I chose this partly because I had a red cabbage in the fridge last night. Oh yes, it's certainly changed colour now. It's gone a sort of salmony, maybe very light rosé colour rather than the bright pink. So it should now smell a lot less as I.
Cheers.
Yes,
Cheers,
it does.
right.
It certainly doesn't smell the same.
Yes, feel free to spit this out if you don't like it.
We've got a spittoon.
There's a jug here. We can use this as spittoon.
Go on. That was grim. Oh
so
man!
What's happened to it? So it's
ruined. That's what's happened.
Oh, that was rank.
so what? It's taken. All that acidity away. What we've now got is effectively a neutral
It hasn't
wine.
just taken the acidity away, Alex. It's taken any semblance of wine away.
Yeah, and it basically tastes horrible at this point.
Drinking a washing up liquid or something like that.
Yes, I may have added a bit too much of this, but the flavours I can still get. You can still taste the alcohol in this, so it tastes like a sort of shot of alcohol, but without anything much else. And now the next experiment is to see if we can put the acidity back with a different acid. Yes. Okay. And so acidity is really, really prized in wines because it gives them flavour. Most of the flavours disappeared as well. And if you're in a really hot climate, the grapes tend to turn all that acidity into sugar, and they lose a lot of flavour. So nothing lost. Now this is an acid that I'm going to add, which is a different acid from the one we had before. So most of the acid in the wine would have been an acid called tartaric acid, which I've got somewhere in here, and malic acid.
You're adding what, lysergic acid? It's a bit different kind of acid, isn't it?
Lactic. So this is stuff that builds up in your muscles when you exercise too quickly, and it tastes a bit like yogurt. Right.
Well, it's gone the right colour again, hasn't it?
It's got a nice pink colour
Let's
again.
go back to pink, so we know it's more acidic again.
Let's right.
Oh, sure, go on, I'll give it a go. Go on then.
It's pretty tart. Still.
Tart.
Yep.
Okay, the smell is back. It smells.
The smell is back. Yeah,
Yep, the smell is wine again.
Yeah, I can smell
Yep,
the
it's
wine
back.
again.
It's back
Wine
to
back, exactly,
it's back to Riesling that we had before. I tell you what, it's a lot less disagreeable than than what we did with the first effort with the bicarb.
It's like one of those those sweeties that are super sour. So the flavours weren't destroyed by that red cabbage goop we put in. They were there.
Just hidden by changing the pH. So as you can see, having a more acidic wine gives the flavours more a chance. But
You're really enjoying that, Georgia.
That was a very fine.
Would you like some more? Top up.
Yeah. So that's what you can do, and of course winemakers do this on a much more careful scale with their acidity rather than just pouring a few things together in a punt.
Right, so that's a really interesting example of how acidity is really important. I have new appreciation for acidity because it did taste absolutely awful, and then the flavours did just sort of come back to life.
Exactly, yes. I bought one more.
Oh, amazing.
Yeah. We don't need to finish all the bottles immediately.
There's one each. Yeah.
Oh, yes. I spy a word. Champagne.
Yes.
Oh my goodness, you're treating us.
Yes, that's a good name in wine. Might just have a glass to catch if any champagne comes out. Let's find out. Oh no, not quite. Sorry, I put my finger over the bottle there to stop it all spurting out. And I managed to get.
This Lewis Hamilton experience there for Georgia.
Okay, right, so there we are. There's a bit of champagne. Right,
Cheers.
Well, cheers.
Cheers, Alex. Now, what's interesting about this is it's got very tiny bubbles.
Do the bubbles change the chemistry of the flavour? Does that make sense? Do they change how we perceive that chemistry?
Yes, so the bubbles, when they're on your tongue and in your mouth, they act as little pockets of air, and it's like swirling your glass. They produce these pressure gradients as they're forming, and they make the wine a lot more flavoursome, effectively, so you taste the flavour molecules. If you leave champagne out for a day, you can get a nice wine, but it doesn't taste quite as nice after you've left it for a day.
Brilliant. Well, thank you so much, Alex. It's been a pleasure to have you in your box of wonder on our Punt.
I'm so glad you came aboard.
It's been great fun. Thank you.
You can come back on the show anytime.
Excellent.
Pause 1 second, because look, our long lost passenger, the person we were supposed to pick up earlier, is over here. Let's pick her up. Now, we're supposed to have got you, Claire Bryant, at Queen's College, and you weren't there. What have you got to say for yourself?
Not a lot, really. What can I say? I just missed the boat.
You really did. But it's perfect timing, because you were going to talk to us about champagne.
I was indeed.
We've just been drinking some, because Alex, Tom, this is Claire Bryant from the vet school at the University of Cambridge, who's also an immunologist, but happens to also know all about wine. So do have a glass of champagne on us.
Thank you very much. Cheers.
We were going to launch the Punt with a bottle of champagne, because we used to smash champagne bottles against boats.
Yeah, so there's really interesting history to boat launching, which goes back thousands of years. So the Greeks did it obviously to wish good luck on the boat, because sailors are a suspicious lot. They used to do this with laurel wreaths and stuff like that. And then through the Middle Ages, it acquired a kind of religious connotation. And at that time, what they used to do is they used to drink a bit and then throw the residual on the boat, and then they chuck the vessel into the water. But that became very expensive, because a lot of these vessels were made of precious metal. So it then morphed on over time into being a bottle of something to drink. And then ultimately in the Victorian era, I think it was, they actually started to use champagne. But it does present some challenges, because the bottles have to be very, very strong, because the gas is under high pressure, so the glass is actually very thick. So if you want to smash a bottle of wine against a boat and get it to break first time, you actually have to score the glass to weaken it, so that then when you smash the glass against the boat, it will actually burst.
So there have been some mishaps then, where people have tried to launch ships and the bottle hasn't broken?
Correct, yes.
Oh my goodness. And what do they do then? Because that's bad luck, isn't it?
Well, they just have another go, I believe. But I have seen some videos on YouTube where this is indeed the case.
So people would actually scratch the side of the bottle to put a weak point in?
Yep. And then when you smash it against the ship, it will burst. So.
You enjoying your champagne?
I am enjoying my champagne. I always enjoy a glass of champagne, Chris.
I'm only asking because Alex rinsed the glass out in the river. Does it taste all right?
Thank you, Alex. Now I will stop drinking it.
Because that was a horrible link to the fact that you are actually an immunologist. So ostensibly, the reason we asked you onto the Punt was to talk about your science. What do you actually work on immunologically?
So I work on salmonella bacteria, which cause food poisoning and are a massive zoonotic disease. So by zoonotic disease, I mean one which jumps from animals into humans. So as I work at a vet school, I'm particularly interested in bacteria such as salmonella, which remain hidden, basically. The immune system doesn't seem to recognise them in animals, but as soon as you eat some chicken, then the salmonella then is recognised by humans and gives you a nasty gut upset.
How does it actually make us unwell when we catch salmonella?
Well, so that's quite a complicated process. So with respect to the salmonella that jump from chickens into people, what they do is they produce a whole series of bacterial proteins, which then invade the epithelial cell, which is the cells lining the gut. And that then causes the cell to become inflamed, diseased, and causes diarrhoea. So it's quite nasty, and it can, in certain circumstances, actually go across the gut and go into the blood supply, and then people can get very sick indeed.
And you're trying to work out how the bacteria evade the immune system, or the immune system attack the bacteria?
There's two things we're trying to do. So one is we're trying to understand how salmonella activates the immune system in people. And then secondarily, we're trying to understand why in animals like chickens, they don't seem to see the salmonella in the same way. And so what is it that's different either about the bacterium or about the host animal and the host animal's immune system that means that salmonella can sit quite happily in a chicken gut and not cause any problems at all?
So the chicken is carrying the salmonella bacterium, but it's not making the chicken ill.
Correct.
But equally, the chicken is not fighting off the salmonella and getting rid of it.
Yep, that's absolutely right. So one of the concepts we have is there some way that we can actually remove the bacteria from the chicken by a vaccine process, for example, or by stimulating the immune system in the gut, such that the bacteria, the salmonella that are present in the chicken gut, are then got rid of, and then they're not available to go down the food chain and infect people.
How are you trying to do it?
Well, we're trying to develop vaccines, and we're trying to develop immunostimulants that would actually do that. But in order to be able to target that in the most correct way, I'm trying to understand how the chicken sees the salmonella, to then see which of the molecules that are best to target, to see if we can then prevent the salmonella from sitting in the chicken gut and sitting in the gut mucosal surface. So to understand how to tackle the problem, we need to understand the biology and the host immune interaction, which as yet we don't fully understand, but it's kind of groovy. There's lots of really interesting differences between chickens and people in their immune system.
Well, I've noticed one or two. I mean, they're birds, we're humans, but is it that in the same way that I've got lots and lots of friendly bacteria living in my intestine, and so my body tolerates them, doesn't get rid of them because they do a good service for me, is it that in a chicken, salmonella bacteria behave like that, and they're almost like a normal part of the bugs that live in a chicken?
Effectively, yes, but what we don't understand is why that is. So there are, for example, some salmonella that humans tolerate and don't cause disease. There are some salmonella species that cause disease in chickens, and there are other salmonella species that don't. And there's obviously complex differences in the salmonella genome, which contributes to part of this, but presumably there are some molecules that are particularly causing pathogenic effects in chickens that are present in some bacterial species and not in others, and those are then different in the bacterial species that cause disease in humans. So it's understanding the reasons why one salmonella is a pathogen and another is a commensal is really of top interest, and I don't really think we're close to understanding that yet.
While we're talking about bacteria, as someone who takes, I'd say, semi-frequent dips in the cam in the nice weather, how worried should I be?
Very worried. The cam is one of the areas that hosts a bacterium called leptospirosis, which can cause a disease called Weil's disease. It's really nasty, so you're going to like this. So it comes from rat urine. It's carried by rats and dogs. We vaccinate our dogs against this disease specifically to prevent people getting leptospirosis. It's really nasty. You wouldn't catch me going in that river.
Just asking for a friend, what are the symptoms?
There are a variety of symptoms. There are a variety of symptoms. At its most severe, it can cause renal disease, so kidney failure. It can cause meningitis. It can cause severe fevers. At its mildest, it will just cause you a severe fever and make you generally feel unwell. It's not a bacterium you want to try and acquire.
Well, on that note, we won't make you walk the plank and get in the water because you might catch Weil's disease. But thank you very much for joining us, Claire Bryant, and also Alex, Tom. It's been a pleasure.
And that's where our journey ends for this week, hopefully without a serious disease. Thank you so much to all of our passengers who took part, and to Izzy Clark for putting the programme together, and of course to Max Thompson from Rutherford's for punting us so expertly.
We will be back next week with a look at biomimicry. That's how scientists are borrowing from what biology does best. Do join us. Meanwhile, from me and from Georgia, thanks for listening and goodbye.